Hello students. Till the time we have dealt with a lots of changes whereas the participating unit electrons works. But today in this lecture we will be dealing with those changes where protons and neutrons, that are the rest two fundamental particles of an atom, participates in any change. And these changes where the participating units are not electrons, these are the protons and neutrons, are termed as nuclear changes. And the branch of chemistry which deals with these nuclear changes is called nuclear chemistry. So that's our today's topic. Here we will be dealing with the nuclear chemistry. As I said initially, that this nuclear chemistry is defined as the branch of chemistry which deals with the changes that occurs in nucleus. So that is our today's topic. Here we will be dealing with the nuclear chemistry. But before we come directly to the changes that occur in the nucleus, first of all we will be taking the idea about this term nucleus. If I talk about this term nucleus, then this term was very first introduced by the scientist Rutherford. Rutherford, in his alpha particle scattering experiment, he defined the nucleus as the very small place of an atom where all the protons and neutrons remain situated. And this very small volume of an atom which has the positive charge due to the presence of positively charged protons, it is termed as nucleus. Since this nucleus contains protons and neutrons, so that is why these protons and neutrons that are remain situated in a nucleus, combinedly these can be termed as nucleons. Now, if I talk about the size of this nucleus, then the size of this nucleus, it depends on the atomic mass number of that element. And the relation, what we can derive for the atomic mass number and the radius of any nucleus, it was given by scientist Rutherford again in his alpha particle scattering experiment. And this relation can be given as, if I am to find the radius of any nucleus, then it is directly proportional to the cube root of the mass number of that atom. Here, if I remove the proportionality sign, then there a constant will come, and this constant is indicated by the symbol R naught with the cube root of this mass number. Here, this constant R naught is termed as Rutherford's constant since it was given by Rutherford, and the value of this Rutherford's constant is in the range of 1 Fermi meter. So here we can see that the radius of this nucleus will be in the range of 1 Fermi meter. According to the mass number of any atom, this radius will change a little bit, but the range will be in the Fermi meter. So now we can give the radius of the nucleus, and this radius of nucleus will approximate in the range of 1 Fermi meter, or we can say it will be approximate equals to 10 to the power minus 15 meter. That is about the size of this nucleus. Now, if I talk about the density of this nucleus, then the density of this nucleus is in the range of 10 to the power 17 kilogram per meter cube. So that is about this nucleus. Now, if we go for the classification of this nucleus, now this classification can be done on different bases, and the very first basis of this classification is, here we will be dealing with those classification that can be done on the basis of number of protons and neutrons present in an atom. This number of proton can be represented by the atomic number of this atom, and this classification that indicates the another thing here, it is the number of neutrons. So this classification is on the basis of the atomic number and the number of neutrons present in an atom. According to this basis, nucleus can be classified in four different categories, and these four different categories are termed as, the very first category is termed as isotopic nuclei. that are also known as isotopes. The second category, it deals with the isobaric nuclei or isobars. The term is used for the elements. The third category, here we will be dealing with those nuclei which are termed as isotonic, and these nuclei containing element will be termed as isotones. The very last category is termed as mirror nuclei. Except these four categories, there is one more special category that is termed as nuclear isomers. So here we will be dealing with this term very first, that is termed as nuclear isomer. Basically, nuclear isomer term is used for those nucleus which have same number of protons, means they will be having same atomic number. If these nucleus containing same number of neutrons, but they will be having the different way of arrangement of these nucleons in the nucleus. Same as we do for the arrangement of electrons in an atom, we consider that there are circular paths around the nucleus in which these electrons keep on revolving. The same kind of arrangement is also considered for this nucleus, and inside this nucleus there are the circular path in which these nucleons, that are protons and neutrons, they remain situated. Now if there are two nucleus which have the same number of protons and neutrons, means they have same number of nucleons, but they have the different way of arrangement of protons and neutrons in this nucleus, then these two nucleus will be termed as nuclear isomers. Now this was in very brief. Now we will be talking about the rest four types of nucleus that we have seen here, and the very first that I am going to start is isotopic nuclei. Basically, isotopes term is used for those nuclei which contain same atomic number, or they contain same number of protons, but they contain different number of neutrons. So if there are two nucleus with the same value of atomic number and they contain different number of neutrons, then these can be termed as isotopic nuclei, and those elements which contain these two types of nuclei are termed as isotopes of each other. Such as, if I talk about the isotopes of hydrogen, then the very first isotope of hydrogen is represented by the symbol H11. The second one can be represented by the symbol H12, and the third one can be represented by the symbol H13. Now if I talk about the nucleus of these three elements, then since the very first has the atomic number 1, so it will be containing 1 proton. Here the number of protons are similar, that is 1 for each. If I count the number of neutrons present in the nucleus of these elements, then since the atomic number and mass number both are having value 1 for this protium, that is H11, so the number of neutrons will be 0 here. If I find the number of neutrons for this H12, that is also known as deuterium, so here the value will be 2 minus 1 and the number of neutrons will be 1. For this tritium, the number of neutrons will be 3 minus 1 and the number of neutrons will be 2. Now if I talk about the nucleus of these three elements, then these are having same atomic number but the different number of neutrons these are having. So these can be termed as isotopic nuclei. The another examples for these isotopic nuclei are, if I talk about the isotopes of sodium, that is with the atomic number 1122, that is 1123, and the last one is with 1124. Then if we go to compare the number of protons and neutrons present in the nucleus of these elements, you will be finding that all of these three will be having same number of protons, that is 11 for each. But if we find the number of neutrons for each one, then here the number of protons are 11. For this one the number of protons are 12, and for the third one it is 13. So these nuclei which are having same number of protons but different number of neutrons can be termed as isotopic nuclei. Now we will be dealing with the second category, that is termed as isobaric nuclei, or the elements are termed as isobars. Isobars term is used for those nucleus which contain same atomic mass number, means the sum of nucleons for these two nucleus will be same, but they will be having different number of protons. For example, if I compare the nucleus of carbon 614 with the nucleus of nitrogen 714, then the nucleus of these two elements will be having same atomic mass number, that is indicated by the value 14 here. So means the nucleus of these two elements will be having same number of nucleons. The total number of nucleons is same for these two, but they are having different number of protons. The very first is having only 6 protons, while the second one is having 7 protons. So these two nucleus are termed as isobaric nucleus. The another example of these isobars are sodium 1124 is isobaric with magnesium 1224. So these are the example of isobars element, and these nuclei will be termed as isobaric nuclei. Now if I talk about the third category, then this third category can be termed as isotonic nuclei, and the elements are termed as isotones. This term is used for those nucleus which have same number of neutrons, but they have different value of number of protons, and due to the presence of different number of protons, there the total sum of nucleons will also vary. Like the definition will be these will be having same number of neutrons, but they will be having different number of protons, and due to the different number of protons, the total sum of nucleons will also vary. Like if I talk about hydrogen 1,3, that is the one isotope of hydrogen, and if I compare this with the atom of helium, that is He24, then if we find the number of protons for these two, then the very first is having one proton, second one has the atomic number 2, so it will be having two protons in the nucleus. While if I find the number of neutrons for these two, then the very first is having number of neutrons, that is equals to atomic mass number minus atomic number, the value is 2, and here again the number of neutrons is, if I go to find the sum of nucleons here, then this mass number indicates the sum of nucleons, and then for the very first one the number of nucleons are 3, while for the second one the number of nucleons are 4. Now if I compare the nucleus of these two elements, then these are having same number of protons, but due to the different number of neutrons, the total sum of nucleons also vary. So these can be taken as the example of these isotonic nuclei. The another example of these isotonic nuclei can be taken as carbon 613, that is one isotope of carbon, with nitrogen 714. If you go to find the number of protons, neutrons and the mass number for these two, you will be finding that these also come true to the definition of these isotonic nuclei. So these can be taken as the example of isotonic nuclei. Now we will be talking about the next definition or the next category of this classification, and that is termed as mirror nuclei. Now we will be dealing with the next category, that is termed as mirror nuclei. Before we deal with the definition of this mirror nuclei, we will be understanding this definition by taking a simple example. If I consider two nucleus, the very first I am going to indicate by the symbol X with the atomic number Z1, and the mass number that I am giving for this element is A1. And the another element whose nucleus we are to study, I am going to indicate by the symbol Y with the atomic number Z2, and the mass number I am using here A2. If I find the number of protons for the first one, then the number of protons will be equals to the atomic number Z1, and same for the second one, it will be equals to Z2. If I find the number of neutrons for the first one, then it will be equals to the mass number A1 minus atomic number Z1. Here I am using the term N1 for the number of nucleus, for the number of nucleons Here I am using the term N1 for the number of neutrons present in the nucleus of this first element. If I find the number of neutrons present in the nucleus of the second element, then it will be equals to the mass number A2 minus atomic number Z2, and this can be indicated by the symbol N2 here. Now, these two nuclei can be defined as mirror nuclei if they follow the condition, and the condition is if the number of protons present in the first nuclei, that is equals to the atomic number of its, is equals to the number of neutrons present in the second nuclei that are indicated by the symbol N2, and the second thing is followed by the and the same thing is followed by the second element also. If the atomic number of the second element Z2 is equals to the number of neutrons contained by the very first element, that is N1, then if these two nuclei follow this condition, and this condition is the number of protons present in one nucleus should be equal to the number of neutrons present in the another one, then only these nuclei can be termed as mirror nuclei. Now this is about the definition. Now if I find the relationship between the mass number of these two nuclei, then the atomic number of the very first nuclei Z1 can also be written as mass number A1 minus number of neutrons contained in the very first element, that can be indicated by the symbol N1 here. Since from the relationship that is required to be mirror nuclei, we have seen that this Z1 should be equals to the number of neutrons present in the second nuclei, that is N2. Then this can be marked at the very first relationship or the very first equation. Now same thing if I do for the second element. The second element has the atomic number Z2, that is equals to the mass number of this element A2 minus number of neutrons present in this, that is N2, and this will be equals to the number of neutrons present in the first element, that can be indicated by the symbol N1 according to the definition of mirror nuclei. This equation can be termed as the second equation. Now from the very first equation we can find the value of N1, and this value of N1 will be equals to the mass number of first nuclei A1 minus the number of neutrons present in the second nuclei, that is N2. This thing I have derived from the first equation. Now if I put this value of N1 in the second equation, then this value will be equals to the second, according to the second equation, mass number A2 minus N2 is equals to N1, and here the value of N1 is equals to A1 minus N2 according to the first equation. From these two values, here this N2 will be cancelled since it is at the both sides, and from here we can see that this A2 is equals to A1. So that is the second relationship for these mirror nuclei. Now these mirror nuclei can be defined as the pairs of isobars, as we have derived that these mirror nuclei will be having same atomic mass number. So these can be defined as a pair of isobars in which the atomic number and the number of neutrons values are interchanged. So that is about the definition of these mirror nuclei. Now if we apply this definition for some examples of this, such as if I am having tritium, that is one isotope of hydrogen, that is H13, and if I compare this with the isotope of helium, that is He23, then the very first condition that you are to check that these two should be isobaric in each other in order to be mirror nuclei. Then these are having same atomic mass number, that is 3 for each. So that's the very first condition that these two have fulfilled. Now if I find the number of protons for the first one, then the value is 1, and for the number of protons for the second one, the value is 2. If we find the number of neutrons for the first one, then the value is 2, and here the number of neutrons are 1. So here we can see that the number of protons present in the very first element is equals to the number of neutrons present in the second element, and same for the second element. How many protons it contains, that is equal to the number of neutrons contained in the second element. So these are isobaric nuclei that have the interchanged value of protons and neutrons. So these can be taken as the example of mirror nuclei. The another example what we can give for the mirror nuclei is carbon 613 shows mirror relationship or is mirror nuclei of nitrogen 713 due to they follow the relationship what I have explained before. So that is about the types of nucleus or classification of these nuclei on the basis of the number of protons and neutrons contained by them. Next time we will be dealing with the classification on the basis of the stability of these nuclei.